Now, just like in the 5-electron group example, here we're going to have to use an expanded octet again because we have 2, 4, 6, 8, 10, 12 electrons minimum being used for this geometry, and possibly more if any are double or triple bonds. So when you have to get up to 12 electron groups, you've definitely got to be able to break your octet rule. So once again, we have to be in the group, in the section of the periodic table where we can break our octet rule by expanding the valence shell. Now, this is a geometry that makes probably more sense than any others, although I do want to point out with the name octahedral. Octa implies 8. And remember earlier I made a big deal about tetrahedral. It was about the number of faces, not about the number of atoms. The reason I pointed that out then is so that we didn't have that misconception firmly rooted in our minds. Because I've got 6 atoms here, at most, and octa implies 8. We're not talking about the atoms. We're talking about the faces of a crystal that we would make with this. You can see that we'd have this front triangle right here. We have the back triangle right over here, back one over here, and the front one right up here. That's 4. And then the mirror image of that down here would give us a total of 8 faces between each of these spots. So if we were to grow lots of these molecules sitting next to each other as a giant crystal, it would end up having this octahedral geometry. That's where the name originally came from, because when we measured these, we didn't know about the atoms originally. What we were measuring was something more about the pattern of the shapes. So the name just kind of stuck. So even though, like I said, this implies 8, we're talking about the faces. Octahedral will have 6 atoms. Okay, so we've got our octahedral geometry. Now we don't have to care at all about which one we substitute in next if we're dropping to an AX5E geometry. And we're going to call that a square pyramidal geometry because you've got a square shape on the base making a nice pyramid going upward. So square pyramidal, AX5E. And you can picture that if we had substituted it for the top one, it's the exact same thing, just rotated differently. So it doesn't matter for that first one. But here's the thing. This electron pair is taking up lots more space than the bonds do. And that means that if we have another big squishy one come in, we want to give it the most room possible to keep it away from this other big squishy one. Place with that space is going to be the opposite side, and so that's what we're going to get. In fact, let me clean up the slide again. So we'll have our big squishy things on opposite sides. That'll be a square planar geometry. Those will always be opposite sides. And so you can see here we'll have a square shape sitting in a single plane, hence the name. Electron pairs go up and down from there. So that's our AX4E2 family of geometries. Now, if we were to end up swapping in one more, no matter what we do, it's going to have to be adjacent to one of the electron pairs. Go ahead and take a look at the square planar and just picture substituting one in. You'll see that no matter where you put the next one in, you're always going to have it right up against the other two. And that means you're always going to have this overall shape. And if we think through what we did last time, we'd say, oh, that's going to be a T-shaped geometry again. And you're right. The book doesn't have a picture of that one. I have it sketched here for you just to have an idea of what that looks like. So that'd be one of our T-shaped geometries. Now we can also end up with a linear geometry as we substitute these in. And that would just look like any of our other linear geometries. But at this point we've got so many missing atoms compared to the number of electron pairs we have. It's pretty unlikely that we're going to see this geometry at any point. And that's one of the reasons the book didn't really focus on these. But just to make sure that we had that completion, I wanted us to see those two as well.